Okay, so in this lecture, we're going to talk about the pH of buffer solution. So, what is a buffer solution? A buffer solution is a solution. There are solutions that resist changes in pH by neutralizing added acid or a base. So, they resist changes in the pH. Buffer solution contains either a significant amount of weak acid and its conjugate base, or a significant amount of weak base and its conjugate acid. That is very important. Weak base and its conjugate acid. For acidic buffer, if a strong base is added, it is neutralized by the weak acid. If a strong base is added, it's neutralized by weak acid in the buffer. If a strong acid is added, it is neutralized by the conjugate base in the buffer. So that is why it's able to resist the pH changes. So how do acid buffers work? They work by applying Le Chatelier's principle for the weak acid equilibrium. The buffer solution contains the significant amount of weak acid molecules which react with the added base to neutralize it. So this is what we're saying. This is a weak acid. It reacts with the added base to neutralize it from water. And the buffer solution also contains significant amount of conjugate base anion, which combined with added acid to make more HA. So uh, after equilibrium, the reaction shifts and hydronium ion remains constant. So that is a principle of acidic buffer. Basic buffer also work with the same principle of Le Chatelier's principle, the same thing. So how do we find the pH of a buffer solution? So um, we have steps in which we can use to write it. To find the pH, we can write the equation for the acid and use it to prepare the ICE table. Then we complete the ICE table using the given initial concentration of the acid, and the conjugate base, which will be provided. Then we can represent the change in the concentration in terms of X, just like we do for our equilibrium concentration, table, the IC table. Then we substitute expression for K in the equilibrium constant expression. And we use our X to determine the hydrogen ion concentration, and we can always check our answer. Another way is to use the Addison-Elsberg equation, which we can find the pH saying which is going to be equal to the pKa plus the log of the concentration of the conjugate base and the weak acid that we have. For example, calculate the pH of a buffer solution that is 0.1 molar in acetic acid. This is a weak acid, and 0.1 molar, and this is the conjugate base that we have. So like we said, we need to write the equation. So this equation is given for, as we've seen in this reaction in my pink pencil. So, and we know that next thing is to prepare the ICE table, so which is our initial change and the equilibrium value. So initially we have for the acetic acid, it is 0.1. So we write it here, 0.1 molar. And we have this to be 0. And for our conjugate base, we have it to be 0.1 molar. So the next thing is we need to represent our change, right? This is going to be negative x, positive x, and positive x. So we can find the equilibrium concentration from our ICE table. It's going to be 0.1 minus x, and this is going to give us x, and this is going to give us 0.10 plus x. So that is going to be our equilibrium value. So we can now write our equilibrium expression for Ka. So our equilibrium expression is going to be, as usual, this, which is our product here, multiplied by our conjugate that we have over our reactants, which is the acetic acid. So we write it this way, and we can plug in our equilibrium value expression into this. So our hydrogen ion is this, so it becomes x, and 0.1 plus x over 0.1 minus x. All right. So, and we know our Ka to be given as 1.8 times 10 to the power negative 5. So we're going to substitute that in. So we have 1.8 times 10 to the negative 5 into our x into 0.1 plus x over 0.1 minus x. So we can assume that x is small. If we assume that our x is small, so if that is true, if our assumption is true, we usually assume that so that we can, solve our equation. So this is still gonna be like, this is small, it's gonna be like 0.1, 0.1. So we have 1.8 times 10 to the negative 5 equals to x is 0.1 over x into 0.1. Over 0.1, right? So this is going to cross out, and our x is going to be 1.8 times 10 to the negative 5. So we can always check if our assumption is right, because by the time you compare this value to your 0.1, it's still going to be less than 0.5%. So our assumption is correct. So we can say that our x is equal to this value. And of course, our x is hydrogen ion concentration, which is going to be 1.85 times 10 to the negative 5. And we can always find the pH of this. So we know that pH is what? pH is negative log of hydrogen ion concentration, right? And it's going to be negative log of 1.8 times 10 to negative 5. If we plug this into the calculator, it's going to give us 4.74. So that gives us the pH. The next example we're going to take a look at is calculate the pH of a buffer solution that is 0.05 molar. in benzoic acid, so this is our weak acid. And sodium benzoate, this is our conjugate base. And we have the Ka from tables to be that. So as usual, again, we're gonna write the equilibrium expression, equation for our weak acid and the conjugate base. And we set up our ICE table this way. And of course, we fill it with the initial concentrations. So from the problem, we know that we have 0.05 and 0.15. So this is going to be, initially, we're going to have 0.05. And this is 0, and this is going to be 0.150. And of course, we express our change. This is going to be negative x, positive x, and positive x. We can find the equilibrium concentration is going to be 0.05 minus x, and this is going to be x, and this is going to be 0.15 plus x. And if you write our equilibrium expression from the equation, it's going to give us Ka is going to be x into 0.15. Remember, this is our product, plus x over 0.05 minus x. Of course, we're gonna assume that our x is small so that we can, solve this problem. So if you assume our x is small, so the equation is gonna be Ka, which is 6.5 times 10 to negative 5, is gonna be equal to x into 0.15 over 0.05. Right. So if you solve for x, x is gonna give us 0.05 times 6.5 times 10 to negative 5 over 0.15. And if you plug that into our calculator, it's going to give us 2.2 times 10 to 5. And of course, we know that our x is our hydrogen ion concentration, which is going to be 2.2 times 10 to negative 5. And the pH is going to be equal to negative log of hydrogen ion concentration, and pH is going to be negative log of 2.2 times 10 to negative 5, and that gives us 4.66. We can use Adamson-Elsberg equation again to solve this. It can be, which we say pH equals to pKa plus the log of concentration of the base over the weak acid. So Ka is given to be 6. Our Ka is given to be 6.5, right? times 10 to the negative 5, we just find the pKa, which is going to be negative log of 6.5 times 10 to the negative 5 plus the log of the base, which we have to be 0.15 over the acid, which is 0.05. So that is from the question. Initial concentration that we have 0.05 and 0.150. So if you plug that into calculator and solve, it's gonna give us this is gonna give us 4.187, and this is going to give us 0.48, and if you add everything together, it's going to give us 4.66. So that is another way we can find that. So that kind of same. All right. So let's take we said Anderson-Esselstyn approach is this. So we just plug in, this is the equation that we have for that, and of course we find the pKa, which is the log and everything that we do. So this is the equation we use for the Anderson-Esselstyn approach. So calculate the pH of a buffer solution that is 0.5 molar in ammonia and 0.2 molar in ammonium chloride. So we know here that our weak base, the weak base is our ammonia, and the pKb has been given. So we're going to use Anderson to solve this problem, this case. So we have pKa. We know that pKa plus pKb equals 14. So since we are given pKb, we're going to use pKa. So we can find pKa to be 14 minus pKb, and that is going to give us 14 minus 4.75. This is our pKb. So that gives us 9.25. So since we know the pKa, so we can use that in Anderson-Esselstyn equation, which says pH equals to pKa plus log of the concentration of this base over the acid. So we know our pKa to be 9.25. We plug it in here, plus the log of the base. So what is the concentration of the base? Here, this is our base, weak base, which is the ammonia, and 0.2 is that of the, okay, so we have 0.5 over 0.2. When you plug that into calculator, it's going to give you 9.25 plus 0.4, and we add this together, it's going to give us 9.65. That is our pH. So this is a best approach to solve some problems involving the pH of a buffer solution. And I hope we can use this to solve as many problems as we can lay our hands on. Thank you.